transistors. So Marcello, please.
Thank you very much, Gregorio. So, good afternoon, everyone. I am Marcello Neto, and I come from the Universidade Federal do Rio de Janeiro, and I would like to thank the organizers for giving me the opportunity to speak about my most recent work. I would like to tell you a little bit about the quantum geometry of tellurene and the measurement that we did in some field effect transistors. So this is our team. We did this work with two professors from UFRJ, Marcos Moutinho and Caio Levenkopf. These two are my students. Caio Edson is my master's student. Pedro Vale, my PhD student. Vitor Velasco is my former PhD student. He's now a postdoc at CISA. We have here Pier Paolo Fontana is an Italian who is now in Barcelona as a postdoc. And we are all theorists, and we learned a lot, quite a lot, with our discussions with the Purdue group, the experimental group led by Professor Pei Deye and Cheng Niu, who was his PhD student. He's now a postdoc at IMEC. So I'm going to tell you a little bit about the quantum geometry of tellurene. So I divided this talk in three parts. So first, I'm going to talk to you a little bit about the phenomenology of the problem. There are two possibilities for the phenomenon I'm going to talk about, which is unidirectional magnetoresistance. So it can be either chiral or polar, so I will discuss the phenomenology. Then on the middle part, I'm going to tell you a little bit about quantum geometry and why do we think that this has anything to do with the phenomenology. And the final part is trying to make you believe that the second part has anything to do with the first part, and we are going to compare with the experiments. So what is this unidirectional magnetoresistance, or as we also call it, non-reciprocal magnetochiral anisotropy? I show here two types of materials. One is polar. You can see clearly here a polarization. It's a many element compound, and this is what we call the polar origin for this phenomenon. But we can also have chiral materials. Here you can see you can have a right-handed or a left-handed crystal. So these two possibilities, they were summarized very nicely by Tokura and Nagaosa in this review. And there are a list of materials belonging to both categories, the polar ones and the chiral ones. I can tell you a little bit about these two. So why is it interesting? As you can see here from the expression of the resistance as a function of all these quantities, this is a phenomenon that brings you, deviates from the linear relationship between voltage and current that we learn from Ohm's law, because here the resistance itself has a dependence on the current. So this brings into play a nonlinear relationship between voltage and the current. And this nonlinear relationship can be measured because it's nonlinear. I can focus on this material here, which was in the previous slide. This has a very clear polarization, which is in the z direction. And because of this structure here, there's a vector product and then a scalar product. You have to prepare the setup with the polarization along the z direction. You drive a current along the x direction. The magnetic field has to be along the y direction. They have to be all mutually perpendicular. And then you can see in the second harmonic, it's a nonlinear response, and you change the magnetic field, you can see beautiful here the phenomenon. If you try to put the current and magnetic field parallel, you see nothing. This is the blue line. So this is the first type of possibility, is the polar origin. And the second type is when you have chiral materials. There is here a number of chiral materials that exhibit the same phenomenon. But here, the relationship is a bit different. The resistance also has a dependence with current, but now it's seen when the magnetic field is parallel to the current. So that's the difference. And I'm going to focus only one in this. This is a very beautiful experiment performed by Riken. He simply got a wire, and you warm the wire, you twist the wire, you drive a current, and if you apply a magnetic field parallel or anti-parallel to this current, you see the phenomenon. It's non-reciprocal. And depending on if it's the Struggerous or Levogeros, you have different slopes here, and this is where the chirality enters into play. So that's why these are called the chiral origin for this phenomenon. So we wanted to investigate this phenomenon in tellurene. There is here a drawing of the type of system that we studied. Tellurene was discovered by the group of Paydaye in 2017. They use a very clever way. It's called hydrothermal growth. They start with tellurite, and then they reduce tellurite in a substance. They use hydrazine as agent, and this produces flakes. The flakes then have to be tuned because they have to disassemble the flakes because they are all together. And then in a solution, there's sort of a conveyor belt of silicon dioxide who on top of which the flakes are deposited. So tellurium, it's a single element material. The tellurium atoms, they arrange themselves in a helical structure, forming a hexagonal lattice. So you can either have a right-handed single crystal or a left-handed single crystal. So, and this generates a very rich band structure. It's a semiconductor. Bulk tellurium is a narrow gap semiconductor. Tellurene is a much larger semiconductor, larger gap semiconductor. But the interesting thing about this band structure is the presence of a vial node at a high symmetry point close to the bottom of the conduction band, and no vial nodes at the uppermost valence band. And the sign of this vial node changes if you have different chiralities. So, of course, because if we look at this, the first thing we thought, okay, it's a chiral material. There's a chiral origin for this phenomenon. So, is it really chiral or polar? Here are the experimental data that Cheng Niu obtained in 2023. You can clearly see the magnetoresistance, a linear relationship with the magnetic field, a linear relationship with the current. If you reverse the current, you reverse the slope. It's all there, but it's all consistent with either one of them. So the only way to really make a strong statement about the origin of this phenomenon is by performing rotations of magnetic field. They've done this in this paper. So let me tell you a little bit about the geometry used. The tellurene flake here lies in the XZ plane. So for us, the Y direction is perpendicular to the sample. And this was the direction that the magnetic field was initially, perpendicular to the film. So if you rotate towards the current, we always drive a current along the helical direction. So Z is the direction of the helices. So if we rotate the magnetic field towards the current at 90 degrees and 270, there's absolutely nothing. So we can rule out the chiral origin for the phenomenon. Nothing happens when the magnetic field is aligned with the current. So, well, it seems that if we are only left with this possibility, we need to have some polarization in the sample. So we also did rotation in different samples. These are the two colors, different samples, and then that's why we have different amplitudes here. Different samples, they have different properties. So in order to establish the direction of this polarization, let's rotate now towards the x-axis, which is an in-plane axis as well. So that's what we did, and we do here the proper geometry. We should have a cosine. They do observe the cosine. And again, when the magnetic field is exactly along the x direction, there's nothing at 90 degrees and nothing at 270. So we were able phenomenologically to determine that there should be a polarization along the x direction. So we were really happy, but where does this polarization come from? This is a single element material. Okay, it's non-centrosymmetric, but is this enough? Then there's this beautiful paper here from the 60s by Richard Zahlen. He was precisely discussing the physics of single element materials like germanium and tellurium. And he was able to prove a theorem using group theory. And as we learned from Ian's talk this morning, group theory is always right. I love that comment. So what Richard Zahlen was able to prove is that if you have a single element material with less than two inequivalent atoms in the unit cell, there is no way you can have infrared absorption. There are no polar modes because basically, although it's also non-centrosymmetric, but there is a symmetry that brings one atom to the other type of atom, and this eliminates the possibility of having a polar mode here. But he was also able to prove that if you have three or more, you necessarily have at least one infrared active mode, and this is known for many times to happen in tellurium. It's at 100 centimeters minus 1, you have infrared absorption. And this is because there are three non-equivalent atoms in the unit cell. But how can we really understand what's going on here? So we have to remember the following. Germanium, what is the electronic configuration of germanium? It's S2p2. So germanium needs 4 more electrons in order to comply with Lewis's octet rule. And that's what he does. It bonds covalently with, in a tetrahedral coordination with its 4 neighbors. And all the electrons are shared in covalent bonds. But tellurium is S2p4. So tellurium needs to make only 2 covalent bonds to comply with Lewis's octet rule. That means that it locally resembles the water molecule because there is an angle here for the bond. And actually, the angle is very similar to the angle in the water molecule, is a 104. But it means that you have lone pairs sticking out of the chain. This is the direction of the chain. So each atom has a couple of lone pairs sticking out. From a top view, number 1 should have 2 lone pairs sticking out here, number 2 as well, number 3 as well. But because of the C3 symmetry, in bulk tellurium, in a unit cell, all this candidate polar electric dipoles, they cancel out exactly. The thing is, we have a flake, we have a film, we have a few layers only. So we did the DFT calculation, and here you can see in blue is positive charge, and you can clearly see per tellurium atom the lone pairs sticking out. And because of the lack of because it's not an infinite system, when we asked the DFT program to give the result of the polarization, we found a very strong and robust polarization precisely along the x direction. Z is the direction of the helices, is pointing towards you, and y is the direction of the growth of the sample. So yes, we found this polarization. It points along the proper direction. There is absolutely no polarization along the helices. This is the red curve here. But then we were puzzled because we found more than what we were looking for. We found a possibility of a small, you can see from the scale, it's 20 times smaller polarization perpendicular to the sample. And then we asked our colleagues, do you see anything if you make a rotation of the field in plane? And they said, yes, this was not on the paper. This was in Chang Niu's thesis. We did here the geometry. We predicted that it should go like the minus the sign of the angle, and this is precisely the minus of the sign of the angle. It's 0 here at angle 0, and it's maximum and minus in minus 90. So we were quite happy because then now we have the full picture of this phenomenology. So yeah, just to summarize, what we have is what Riken had predicted a long time ago that should happen. Every time you try to drive a current across perpendicular electric and magnetic fields. So this, again, this is another brilliant work. He demonstrated this, demonstrated this using a silicon field effect transistor. He applied a static magnetic and electric field externally, driving a current, and then he was able to observe this phenomenon, linear with the current, linear with the magnetic field, and then he made a conjecture. Where is this coming from? This is coming from relativistic corrections to the traditional magnetoresistance that gives you this triple product or mixed product here with the perpendicular B, E, and V. This is an effect that he had himself discovered driving light across material with perpendicular electric and magnetic field, and he observed that the refraction index was non-reciprocal, and then he just thought, well, if this happens to the light wave vector, this also should happen with the K vector or a current. So he predicted, he measured, and he conjectured the form. He did absolutely everything. So our work was, the plan of attack was set. We have to use some framework. We chose Boltzmann transport equations to calculate the nonlinear conductivity. So we want to calculate the current density. We focused on this term here because it has to be nonlinear in the electric field and linear in the magnetic field. So basically, our task is to calculate this G tensor. But we want to compare with second harmonic measurements and normalized, and this was the expression used in all these feats that we done before. So it's not enough to calculate this G tensor. We have to divide by the conductivity because this is the parameter I want to compare with the experiments. So bear with me. We will calculate this tensor, but then we have to divide by the conductivity. So this was the first part, the phenomenological part. Now I'm going to give you a quick refreshment about what's the warping of reciprocal space and the hybridization between Bloch states in this warped space. What does have to do with what I'm talking about? So we've heard Joe Missy's talk yesterday, Tobias yesterday, and yours today talking about metric and how to measure distances in a curved space, in real space. But this story about quantum geometry is, I like this figure here from Thais' science. I stole, and I modify a little bit your figure. I hope you're not mad with me. But this is how you warp reciprocal space, and this change how you measure the overlap between the Bloch states in this warped space. So quantum mechanics is a geometric theory. We know how to calculate distances. There is a metric tensor that appears here, but as you can see, this is not gauge invariant, so it's not yet ready to be used and compared to real data. So, but we can just make a calligraphic quantum geometric tensor here by subtracting the Berry connection, which is the standard definition. And we have an expression, a final expression from the quantum geometric tensor, which is gauge invariant and is ready to be compared to experiments. So the quantum geometric tensor, it has a real component, which is the quantum metric. It has an imaginary component with the more common Berry curvature. It's normally written down this way. And if you have a 2x2 Hamiltonian, like the one for the conduction band of tellurene, you can always find a basis of identity and Pauli matrices, and then it becomes a straightforward way to write these quantities. Once you know what is this D vector here, you simply put in Mathematica and you have all the expressions. And this quantity, the quantum metric, has been claimed to be behind several of these phenomena here. So this was my brief introduction to the problem. To summarize, we do have a Weyl node at the bottom of the conduction band. What is this vial node doing for us? It's providing not only this hedgehog-type texture for barrier curvature, but it's also providing us with geodesics in reciprocal space. And if the quantum states are confined to flow along these geodesics, this can bring us nice physics. So, yeah, this is the quantum geometry. So this is everywhere that the phenomenon has appeared. We are going to make a connection here, longitudinal, with a quantum metric dipole. So in order to understand how can we do a proper calculation, a concrete calculation, this was done by Daniel Kaplan. He simply started with an unperturbed Hamiltonian and introduced the electric dipole coupling. Then, as usual, you perform a unitary transformation to get rid of this term, and you generate a quadratic dependence on the electric field. It happens that the coefficient of this quadratic term is precisely the quantum metric, and this is how the quantum metric modifies the band dispersion. And again, from Thais' science, this is how, if you have a dipole in the dispersion relation, you change the velocities and you can have a non-reciprocal effect. So we, from the band dispersion, you just take the gradient of the full band. You usually have the band velocity, the anomalous velocity, which is related to the barrier curvature, and this new contribution, which is quantum metric dipole related. It's a dipole because derivatives of the quantum metric. It's a new contribution to the velocity that should be included in the calculation of your nonlinear conductivity. So if you talk about nonlinear conductivity, you have several contributions. You can use the fact that the nonlinear conductivity goes with the square of the linear one. And if you get this data, you can see here, this is this material. Also, this is Thais also worked with this material. And if you try to measure the longitudinal voltage and the Hall voltage, in the first harmonic, there is only the longitudinal part and nothing in the Hall channel. But in nonlinear response, you have the two responses. And if you put them together in this diagram, the intercept here is a direct measure of the quantum metric. So this is just to give you an experimental evidence. So what we did was, our task was actually simple. We, sorry, this stopped working. Yeah. So we used Boltzmann transport equations to calculate the current with the semi-classical equations of motion. We included all the terms here. This new term involving the quantum metric dipole, we called the Christoffel symbol because it's also cool to call it a Christoffel symbol. And, but here, in the electric field, we included not only the AC electric field generated by the driving current, but also the DC static electric field related to the polarization due to lone pairs. And when we do this, I'm going to skip the details. We calculate the perturbation to the distribution function, the correction to the current. You can already see here the cross product between the polarization electric field and the magnetic field, and then we calculated the G tensor. So let me now bring the second part to the first part. So this is the final part of the talk. We do have a 2x2 Hamiltonian. We know all the coefficients since half a century ago from magneto-optical transitions. Then we can calculate the D scalar sigma, we calculate the velocities, we calculate the Christoffel symbols. We go through, this is an ugly calculation, but actually it's simple. Because we are restricted to the Fermi surface, this is nothing but power counting of momentum. And then if we recall that momentum is square root of chemical potential, we have this scaling here. I told you not to forget, we have still to divide this G tensor by the conductivity, but we have measurements of the carrier density as a function of applied gate voltage. This is a linear relationship. Then we know how the carrier density depends on the voltage. If we divide G by sigma, we were able to obtain this, this law here, 1 divided by voltage to the power 5/2, which is precisely the red curve here on top of the data. So I would like to call your attention that the ratio that is being plotted here is a ratio of two conductivities, a nonlinear conductivity divided by a linear conductivity. It should not have an explicit dependence on the number of carriers. And as a consequence, not have an explicit dependence on the voltage. And yet, it decreases. And our explanation is because when you gate, you are moving away from warped regions, you are moving into more Euclidean regions of space, and the effect disappears. So, last 2 slides. What about the valence band? Well, the experimentalists, they did the same experiments in the valence band, which contains 0 nodes, and the effect is there. And then you can say, well, Marcello, you just wasted 25 minutes of our time trying to convince us that everything is due to this vial node, and then it's all there in the node field. Please don't answer that quite yet. I have one more slide, because Claudio Iacovelli did the full calculation. So to say that there are no nodes in the valence band is an understatement. This, I just showed you in the previous slide, the uppermost. It's a much more complex structure. There is a vial node at a high symmetry point and other band intersections. He solved exactly, fully the problem, but we can do second order perturbation theory. We know the hybridization matrix elements. We know the distance. We can do T squared divided by the energy. And this gives us this new scaling law, which it corresponds to this blue line here. And then don't get fooled by how the uppermost valence band looked like. Solve the full problem, and it's going to appear. It's much smaller. It's 1 order of magnitude smaller. It's precisely because the vial node is deep down, but the effect is there. So with that, I thank you very much. And
Great. Session is open for questions. Okay.
Hi, thanks. So about basically the main takeaway is that you just, the only thing about the top valence bands, right, you might be fooled. Is this a consequence from the fact that you're looking explicitly at the nonlinear response of the system? Or?
Not really. That's a very good question. If you remember, okay, I think this is enough. Here, there are these blue and red arrows. Mm-hmm. I didn't mention this, but the thing is, this valence band has this Campbell-Back structure, but this is like spin momentum locking as well. It comes from the node down below. Mm-hmm. It comes from second order perturbation theory, but there is spin momentum locking. So even there is this Furukawa paper from the 2020, I think. If you drive a current, you can measure a magnetization. So this is current-induced magnetization. He did this by analyzing some NMR spectrum and NMR shifts. But, and this is a linear phenomenon. So it's not exclusively to nonlinear phenomenon.
I see. Thank you.
No problem.
Okay.
Thanks, Marcello, for the nice talk. So please correct me if I'm wrong. So the effect appear in both cases for the valence and the conduction band analysis due to the fact that your bands are anisotropic. And because of that, the barrier curvature and the barrier connection are no zero. And because of that, you go to get those two contributions, the anomalous velocity and the another one that is the second derivative. So at the end of the day, I was wondering if it's in fact due to this well node or just because your bands are anisotropic. Thanks.
Thank you, Diego, for your question. It actually, this band structure, they have the two things. They contain a vial node, and they are indeed anisotropic. So in this Hamiltonian that I showed you here, So the coefficient C is different than S. So C is along the X direction, and S is along the Z direction. They are not that much different, but they are different. So there is an anisotropy. But if I didn't have the vial node in the conduction band or buried in the valence band, there would be no effect, because then the quantum geometric tensor would be 0, essentially. So it's actually not because of anisotropy, it's because of the quantum geometry. The anisotropy only makes it more interesting, the phenomenon.
Thank you, Marcello, for the very nice talk. Just to make sure I didn't miss anything, so in your case, because you don't have PT symmetry, both barrier curvature and quantum metric contributes to your effect, right?
Yes.
And in the very end, when you show the scaling that you had, that has to do with the cone, right, I think it's further ahead, when you show that you have the vial cone deep in the valence band, but you can account for the scale, yes.
Here.
Yes, exactly. Yeah. So when you do this approach, do you still think of an effective two-band model or you consider the entire occupied manifold?
Yeah, that was a fight between Brazilians and Italians, because I told Claudio, we can do loading perturbation theory, we can generate an effective 2x2 Hamiltonian, and then we have all the mathematical code ready, and he said, no. And I said, okay, so what do you want to do? I'm going to solve the full problem. So he solved the 4x4 problem throughout the entire Brillouin zone numerically. And then he was a bit cocky, because then he said, I did, by the way, the loading, and they both agree. So we are writing this up, and we are going with his full solution. But yes, you can derive an effective 2x2 Hamiltonian, and because of this energy difference here, the results are very similar one to another. Because loading effective theory works better if the other states are very far away from where you want to live.
Thank you very much.
Thank you.
Okay, one last question before we move to.
Very nice talk, Marcelo. I think actually my question has to do with what I just said, that so let me ask my question. So you have just one vial node in the valence band or in the conduction band, right? So because typically you have two. So is this related to the type of symmetries in your material?
Yes.
And if you would have two, which is the typical situation, would you still have this effect?
That's another very good question. So the thing is, I don't have the full band structure in one plot, but yes, as you said, we need to have two vial nodes of different charges. But as Thais said, because here it's a time reversal invariant. We are breaking inversion. So the vial nodes are not splitting momentum, they are splitting energy. So we have this one for the conduction band, and then we need to have the other one for the valence band, and they have precisely opposite signs. And this is why, by the way, we get this curve up here. The first time Claudio did the computation, the blue curve was like this, was with the other curvature. And then he said, it's all wrong. And I said, no, but did you change the sign of the vial node, because it has to have opposite sign? And then we had the curve flipped back. Yes, these are the two pairs. There is no separation in momentum. This would be the case if we broke time reversal symmetry.
Okay, so let's thank Marcello again.